how to look at or mitigate some of those problems, or what could be our strategies so that those problems do not have impact on the final task, like smoothing and so on. These are things that we looked at. So today, and also before that, we looked at different kinds of representation techniques for words. And today what we'll look at is contextual embedding, which essentially we will try to incorporate some learnings from the language modeling topic that we covered. So when we spoke about what to wear or glove, this kind of techniques, we saw that there is one representation, one vector representation for each word, right? Now, irrespective of what is the input sentence, the representation of the word does not change. Even if in the same input, the word is present multiple times, every time it will get the exact same representation. So that means the representation of the input token or word, it does not depend on the context in which it is appearing. However, there can be situations where if we consider the representation to be indicative of the semantics of the word, the meaning and the role of that word, then we expect that it should change depending on where it is present. That means the context should be taken into consideration. So today we'd look at how do we incorporate context for getting these representations. So context is important. If you look at these three sentences, like context is key. I lost the key somewhere in the garden, and you need to generate a SSH key pair. So the word key is present in all three sentences. However, the meaning is different. So in the first sentence, key means important or crucial. In the second one, the key is an instrument which is used to open a lock. And the third one, when we say SSH key pair, we are talking about security password, and in that sense. So the meaning is different, but in case of non-contextual embedding like word to wake or glove, in all three cases we do the same dictionary lookup with key as the key, and we get the value as the vector, so it does not change, which we feel is something that can be avoided. Then if you look at another example, kids went to play outside. Croatia play Germany in the next match, and I never acted in any play. So here also the term play has different meanings. The first one is regular activity. So that is play. The second one, when we say play, I mean, it is a bit closer to the first one, first sentence, the meaning of play in the first sentence, but it is a much more formal and professional in a specific match or a specific tournament. So that way, this play is different from the play that we see in the first sentence. And then the third one is an act of drama. So here the meaning is different, and you can actually create many such examples to show that words change their meanings depending on the context where they appear. So context is important, and how do we represent the word based on the input context? So that part is called actually contextual word embedding or contextual representations. And these representations can be learned in many different ways. So yeah, so there were many different architectures which have been proposed for handling this contextual word embedding. Today we will look at some of them. So if you remember, we talked about RNN. We also talked about this kind of diagram during our discussion on language modeling. So when we talk about RNN, essentially the structure of RNN, the operations that happen in RNN influence or help in getting contextual word representations. How we in this diagram, when we look at this is an RNN cell. So each RNN cell takes two inputs. One is the context so far, representation of the context so far, and the other one is the current input. Okay? Now, if we consider that we have an input text which have been tokenized. Now for each token, we have the token representation which comes in and the current state of the system. So based on these two things, we learn an output representation which is indicative of the representation that or the input that we have seen so far. Input that we have seen so far, and one more representation that is covered by the current input that we are looking at. So it has two different inputs, and if we see that, just give me a minute. If we have the same word in different inputs as we have seen in the previous slide, we will see that, when we look at the word play, before that we have seen the words kids, went, to, and here when we look at play, I never acted in. Now because of the different words that the model has seen before looking at the word play, these vectors will be different when we come to the word play in these two different sentences. So essentially, RNN kind of structure automatically allow us to incorporate context in getting the representations. So that's what has been mentioned in the bullet points. In LSTM or RNN, representations in one cell is affected by the representation of the previous cell. Okay. Now, so these pretend representations, sorry. So these representations can then be used for our further downstream tasks, which could be like sentiment analysis or classification or whatever. Now, this can also be called as the language model representation. So if you look at how this cell is fine, and intuition wise also seeing that okay, every time we have a new token, the output changes. Even that understanding is fine, but how do we get these representations? So from here to here or here to here, these mappings are governed by certain parameters which are here, right, inside the cell. Now, how do we get those parameters? So we need to expose this model to certain task. And when we say certain task, there will be an input and there will be an expected output. Now, my question to you is, can you suggest a task that can be used for training this RNN to get the contextual representation of the different words? Let me repeat the question. So we want to train an RNN so that we can get the contextual representation of the words from it. So can you design a task so that we can train the model to give us these contextual representations?
Masked word prediction.
Can you elaborate on that?
we can mask some of the input and then try to predict those in the output.
Okay, and how will the model determine those masked words?
So because we already know the label, like suppose on in this example the favorite season. So because we know that the prediction should be season there, and then from the embeddings, I think we can calculate the loss and see if it predicted that word or not.
Okay, anyone else wants to try?
Next word prediction task.
And how will that happen using this model?
Um, Maybe we just take until t-1 time steps and then try to predict t time step. Via
How will you utilize this architecture, what you see on this slide, to make that prediction? Can you explain the sequence of operations for doing that? Oh, yeah, so what you said is that we have seen the first t-1 words. Now we want to predict the tth word, right? So what are the steps that will happen according to this architecture?
Taking the bigram model, I think like my we are inputting the previous word here, my, and then based on that we are identifying the weights, and also the based on those weights we are doing the prediction of the next word here.
Okay, so we have got a few responses and all of those are actually correct. But when we try to break it down into the individual steps which the model is performing, we still see there are a lot of step jumps which is happening. So let me try to add those missing steps. So suppose the model has seen my favorite and we're taking the next word prediction task. So after the model sees my favorite, we expect the output is season because the next word is season. So what will happen is that the system will look at the word favorite every time it is looking at one token. So when it looks at the word favorite, firstly, it will try to get an initial embedding of the word favorite. Now this initial embedding can come from word2vec or glove. Okay, so this is that embedding matrix. We multiply it with the one hot vector for favorite. So essentially what we get here is the representation of the word favorite. Now this is the RNN cell, which is similar to what we see here. So it has two inputs, right? One is the current representation of the current word, which is this one, and the other one is the context. Now this context is coming from here. Okay, now this is the WH, which is the context, and this is the W, so which is actually the parameter associated with the content. Now this input and this input together will uh, determine what will be the next context and the representation from here. Okay, so if this context is a t-1 and this is x t, so it can be something like wh into x, sorry, a t-1 plus we into xt and maybe some other transformation function like tan h on top of that. So finally we get this, we get an output from here. Okay, now remember this is an output, but our final goal is to predict the word, next word. Now we have a vector, but from this vector, how do we go to the probability space? One simple trick, one simple step could be like, from this vector, you project it to that vocabulary space. Now, if you have D, if the number of vocabulary, sorry, if the dimension of this is D and the number of words in the vocabulary is capital V, then we can simply multiply it with a vector with a matrix of dimension d cross v, so that the target is a 1 cross v dimensional vector, which can be, and on that we can apply softmax so that it looks like a probability distribution, and from that we can pick the next word. So this is how this model can uh, predict or suggest the next word. And in this process, there will be multiple parameters which will be involved. Say, for example, with this history, there will be one parameter. With this input representation, there will be one parameter. And when we from here to the vocabulary space, when we go, so there also there could be one parameter. There could be different biases which could also be there. And these will be the sequences of operations finally that will lead us to the prediction from the model. And then we know what is the prediction, we know what is the expected output. Based on that, we can compute the loss, and this loss can be backpropagated so that all these parameters can be trained. So this can be called as the language modeling task or language modeling objective, because if you remember, in the language modeling, one way of modeling the task is to predict the next word given the previous words, right? So that's what we are doing here. So this is the language modeling objective. And after training the model with many such input-output pairs, finally the model will converge to, the parameters will converge. So these representation, and now all these parameters can actually be frozen. And when we say all these parameters, and this one, this one, this one, and this simply unrolling. So this parameter is same as this parameter and this parameter and this parameter and so on. So now when we feed any input, we can simply make use of these learned parameters to get the corresponding output, which will be the representation, contextual representation of that word. Now this contextual representation, just because we have used the language modeling objective to train this model, can also be called the language modeling representation. So one can also combine this language modeling representation with the pre-trained representation based on word-to-vec or glove. So there can be situations where people would like to use word-to-vec or glove, and there can be situation when where they want to get only the LM representation, or there can be situation where people would like to prefer combining both these representations. All these are actually valid. Only thing is that if we only use that, so when I write pre-trained here, pre-trained means non-contextual. This I'll modify this part. Yeah. So we only use the non-contextual, it's non-contextual, but the moment we include LM, it becomes contextual. So there was one work in 2017 where people showed at the time that we can combine these non-contextual and contextual representations to get a better performance. So this task was based on named entity recognition. So what they did is, firstly, based on unlabeled data, they trained a word embedding model. This word embedding means word-to-vec kind of model. And then this is recurrent language model, like the one we saw in the previous slide. So now when you have a new word, new input, this input you feed to word embedding model as well as the recurrent RNN model. So for each token, you get one representation from word-to-vec and one representation from this RNN. And these two, this word embedding and this language model embedding, these two things you can combine. And this you can fit to a sequence tagger to get the final level. So when they showed that, okay, it works well for sequence labeling task. So that is one more thing that we would like to mention. If needed, you can combine, you can fuse multiple representations, multiple views also. Okay, so this was one way of getting the contextual representations. And
So one
then,
question.
yeah.
Okay. So this LM embedding that we have trained, so doesn't this already has the information of the token based representations? because that's just we had already inputted the word embeddings like word to vec or glove when we trained this LM embedding. So when we try to take two different embeddings, we should take those embeddings which basically have bring about different information for a particular word token. So just a question on that.
Can you repeat the question?
So, well, LM embedding basically was fetched when we, inputted this word embedding itself, right? And we trained it on the base in this slide, right? So we inputted the word embedding and then we trained these WH values and then we got the weight values for this LM embedding, right? So doesn't this LM embedding already has the, this information which is captured by the word to vec or word embeddings?
Not
So
really.
why?
Not really. See, uh, so typically these models are trained with so much data, right?
Mhm.
So what you get as the contextual embedding can differ drastically from what the input was there. Number one. Uh, Secondly, as we saw that, okay, from token to token, we expect these, yeah, from token to token when we go, here we get a different representation. Here we expect a drastically different representation from here, right?
Mm.
So whatever we had initially at that non-contextual representation, that will mostly be wiped out. So,
Mm.
so that's one thing. Second thing is that when you looked at the task of named entity recognition and so on, you may still expect that for certain locations, venues, person names, and so on, it might be better, because when we talked about, say, proper nouns, when we talked, yeah, so we can refer to, person, organization names, places, and so on. Their representation we do not expect to change significantly. However, NER can also have many other kinds of entities which are not proper nouns, so there things may vary. So essentially it tries to combine the, good parts of both the worlds. For a completely
Okay.
different task, we may not see similar kind of improvement by combining non-contextual and contextual.
Because I had done the same experiment earlier. So, by concatenating the word embeddings and the LM embeddings earlier. So, I didn't, with respect to the NER task, it may, result some improvement because there are some tags which are basically independent of each other, and their word embeddings may bring about those, relevant features. But, you know, for can't just the LM embedding be, sufficient?
It may vary from task to task. For some tasks, you may see a benefit. For some
Mm.
tasks, you may not see.
Okay.
Okay. Any other questions from anyone?
Sir,
Yes, sir, please.
what is can you go back to the previous slide? Sir, here U matrix is the final embedding that we are getting, right? For each word.
No. U is to take this embedding from here to the vocabulary space.
So these edge hidden states are the contextual embeddings.
Yes. Yes.
So like in Glove or Word2Vec where we had two input and output representation for each word. Here we don't have that.
That's that's right. Yeah, that's right.
Sir, for training this LM embedding, uh, you told that there are like we can also train without word embedding input, but we need some kind of embedding to convert this text into numerical format, right? Otherwise, how do we provide input if we do not use embedding to train the LM model?
This embedding can be the word to vec or glove embeddings.
Yeah, so I mean, any kind of embedding is required, right? To train a LM model, first we need embedding of word embedding.
Yes, so you can also, I mean, and that way you can give the models a bit of warm start. Otherwise, you can also get started with 0, 1, with some
Oh,
other perturbation.
just the random.
Yeah, random. But since we know that word-to-wear glove kind of models are trained with large amount of data, if we feed it, we can expect that the model already has some understanding of the words at the base level. And then, yeah, that needs to be further modified. That will happen as part of this exercise. So possible convergence will be faster.
So I have similar kind of question. So now we have already given this word embedding as an input. Then in the next model, again combining this word embedding in parallel, what it will bring, because we have already given word embedding input in the recurrent model language itself.
So we expect that if these three sentences are fed to the model, the representation of key here, the representation of key here, and the representation of key here, they'll be drastically different, right? That's our
Yeah,
expectation.
that I understood.
That means, although we started, I mean, for all these things, we started at the same point. Finally, it's coming quite different. That means somehow we have wiped out that information to some extent. The original this representation. So what
We
they saw
wiped out or we
was
improved on that information.
improved. See, improved we can say, but whatever is the original thing here that we fed and whatever we are getting as output for this, they're completely different, right?
Yeah.
So be it improved or whatever, I mean, that information is not there present at this point in a significant manner.
Okay, got it.
Okay.
Thank you.
So if it can be reinforced in some manner, that could be beneficial. So many times in neural networks also we see skip connections, right? So
Yeah.
this can be also viewed as a skip
Skip.
connection in some nature, some manner.
Yeah, yeah. Makes sense. Thank you, sir.
Okay,
And so
so
in the next, in this particular example, in this particular slide, um, how are we correlating the above slide, sir? I mean, like, there we are doing the word representation and giving it to the RNN. How do we correlate that with this particular representation that we are having on the screen? I mean, the figure that you just explained, the flow diagram, the one, yeah, this one that you just explained is quite clear. But how is it translating it to the slide, the next slide? Sir? I mean, like the input of the word sequence is going into the RNN as per the other diagram that we just talked about. Whereas this one, both are actually going in parallel. The input is the recurrent model is the unlabeled data rather than the word vector.
so this is the input. Okay, then
Yeah.
New York is located, and suppose when we see earlier what happened is that we have an input, uh, we can pass it through word to vec, which is nothing but a dictionary lookup. We get a output representation, and next from the what we saw in the earlier slide, we have the RNN based representation. So let me call it the LM, and this will give another representation. So this is a lookup, and for language modeling, see, when you say New York, this H will be the representation of the York. Till this point, is it clear?
Yes. Yeah.
Now suppose these two things we have packed together, and these also we have joined. So the word York, when we see, or any token that comes, we send it in two different routes, and we get one representation from word to vec and another representation from this language model. Now we concatenate these two. So that becomes the representation. I mean, this is coming from word to vec, this is coming from language modeling. Now we get a representation for the word York. And then we can pass it to a classifier to say, okay, what is the final label for this one?
Okay.
So then the next word is. So the word is again will pass through word to vec, and we'll also pass it through this language model. Now remember, this language model has seen the word new and York, and it is now having a contextual representation of the word is, and here is the regular representation. So this part will keep looking at the context and give contextual representations, and this will give the lookup based representation.
Okay. Okay, sir. Got it. Yeah.
Fine. So let us move forward to the next mechanism. So essentially what we see here is that this is one layer of RNN. So input is here and we get some, we give input, we get some output. So we can write it as RNN and for each input that we get, for each input that we pass, we get an output. So for each token, if there are n tokens, we get n outputs. And what we can do is that we can also constrain that the dimension of the output representation will be the same as the dimension of the input representation. What does it mean? So if here we have 512 dimensional input vector, here also we want 512 dimensional output vector. Now, if that is the case, then we can plug one more RNN layer on top of it. And since this output represented, the dimension of this output is same as the dimension of this input, now this can be considered as input to another RNN, which is actually having the similar kind of architecture as this one. So now we get another representation here. If we want, we can stack one more RNN on top of it. Again, we can do this if we constrain that the output dimension for each vector will be same as the input dimension before it is passed through RNN. So like this, we can stack multiple layers on top of each other. So this is called multi-layer RNNs for representations. So this paper, so we'll look at the exact thing which was mentioned, the architecture which was there in this paper, but essentially it is nothing but this architecture. You have one RNN and you stack together many different layers on top of it. So they call it actually they used bidirectional RNN. So in this case, we had this flowing in one direction context, but we can also have context flowing in backward direction. Right? So this is the forward RNN, we can have a backward RNN. And if we have this bidirectional RNN, then the representation of a word can be the representation that we get from the forward RNN concatenated with the representation that we get from the backward RNN. Now, like that, if we do, so that becomes bidirectional RNN and language modeling with bidirectional RNN. So this model they trained on 1 billion English word benchmark. This is from this one. So, and this becomes now the objective function that they want to optimize. So as mentioned, BiLM combines both a forward and backward language model, and it jointly maximizes the log likelihood of the forward and backward interaction. So what is happening is that, so here T1 to T1 minus 1, this is given. Based on that, we are predicting Tk. So this is going from left to right. 1 to k minus 1 we have seen. Next word Tk we are predicting. And also here there are different parameters. So this is parameter for that forward RNN. And these are the parameters of the softmax layers here. And this X could be the input token representation, the parameter associated with that. Okay, so this is the forward task, and for the backward conditioning, backward model, Tk plus 1 to n, that is the right context is seen, and we want to predict the previous word. And these parameters are the backward RNN parameters. Theta x is the token representation parameter, like and the initial level what we are getting. And theta s is the softmax, because finally from the representation we need to get to the vocabulary space. So parameter associated with that. Now we're combining both these. So that is about this bidirectional RNN, and this we can do in an stackwise manner. These RNNs can be bidirectional RNNs, and we can combine multiple of them. So it becomes bidirectional multi-layer RNN for language modeling. Now, this model they named as ELMO, which stands for embeddings from language models. So again, we have an input. The input is tokenized, okay, and for each word we get an initial representation. And note that the arrows are bidirectional here, and these are individual RNN. LSTM is one type of RNN only, LSTM cells, and we have these bidirectional connections. So for each word, this LSTM gives two representations that is shown here. And this two representation means one is coming from forward LSTM, another is coming from backward LSTM. But we essentially combine them and we feed it to the next LSTM. And again, this also produces a forward representation, backward representation. But again, whenever we look at it for the further processing, we combine them, concatenate them. So this goes from one layer to another layer and so on. But the question is, for a single word, we now have many representations, right? We get that initial representations, which may come from even non-contextual embedding. We get a representation from layer 1. For the same token, we get another representation from layer 2. So the question is, which one should we use? So what they said in this paper is that you can take a weighted combination of all these. So I into the representation getting from obtained from the layer 2, j into the representation obtained from the layer 1, and k into the representation obtained from the at the initial layer, the 0th layer. So we can take a combination of that. So here also we see that it's not concatenating, but in earlier slides what we saw is that they are trying to make use of both word embedding and LM embedding. Here also they have used it. So, and this combination they say is more powerful. So what we see here is that we are using stacked LSTMs, and each LSTM layer I gives a representation HI for the token TI. And the final representation H is a combination of the representations coming from different layers. So H is a function of this one, H0 to HL, assuming there are capital L number of layers. And this aggregation function, there can be many different choices. What they have used is the weighted combination. Now, yeah, so this combination has many choices. The thing is, this is the basic language modeling. This is the architecture that we can expose to the language modeling task, and we can obtain the parameters for these different LSTMs. And finally, these representations, what we get, we are getting it for using them in some downstream task, right? So how do we use them in downstream task? So it can be, again, depending on the task, it can vary. So the same thing being shown pictorially. So there are three representations, assuming that there are two layers of LSTM. So this is the initial, then this is the layer 1 representation, this is the layer 2 representation, and is coming in forward direction. Similarly, for that same word, initial representation, which will remain the same, is from the backward layer 1 representation, from the backward LSTM, the layer 2 representation, and then we combine them. Same thing being shown in a different way, but a couple of additional information here is that the serial layers we concatenate, and then these weights can actually be task specific. So for different tasks, you may expect that different layers should be given different weights. And there are some experiments that people have done, and they have seen that when we try to get something which is an overall, which is where we would like to get an overall meaning of the input. So in that case, the higher layers may have better weights or larger weights. For example, suppose we want to know the overall sentiment or the classification. So that means we need to get an overall idea of what is there in that entire sentence. Now, in that case, the higher layers can have larger weights. On the other hand, there could be some other tasks where we need to look at the things in a more fine-grained manner, say named entity recognition or part of switch tagging. In those cases, what they have seen is that higher weights for the lower layers, that works better. So these weights can actually be task specifics. These can be hyperparameters. These can be learned using Lec6, or there can be other ways of learning it. So that's what. And in their experiments, they also said that, okay, based on the task, we can add one more parameter or hyperparameter at the beginning. And whatever representation we get, even after this weighted aggregation, we can further multiply with some other task, a task specific parameter to get the final representation. So Elmo can give task specific representation because these weights can be task specific, and a downstream task learns the weighting parameters. So if you have a downstream task, when you train for the task, you can actually adjust these weights during backpropagation. And unlike usual word embeddings, Elmo is assigned to every token instead of a type. Now this type can be considered as word, a word to vec, assigns a vector for a word. And here we are not assigning a fixed vector to the word, but to the token. So that is so this is
Token is a word or is a character?
what?
In Elmo, your token is a word, right? Uh, So I just want to know the difference. This
Difference
line.
between token is every occurrence of a
Mm-hmm.
word. Every occurrence of a word is a token.
Yeah. But basically, it doesn't give the character-based, differentiation between any of the two tokens, right? Or positional importance.
So suppose
So
this is suppose my input is share your or generate your private key and public key. Okay? Then after, so we have two mentions of key. These become two different tokens. Then we have context is key. This is the third token for key. I lost the key. This is the fourth token for key. So every single occurrence of a word, every single occurrence of a term from vocabulary is a token. So and it can be in one single input or across different inputs. So if you remember in word2vec, we had this summation over 1 to t. What was
yes.
this t? This t was the number of tokens. That means the total number of. So if you combine everything, you split based on delimiters or whatever, the size of the final list that you get is the number of tokens, which means for every word, whenever it is appearing in the input or input collection, we consider it as a separate token. That is the difference between token and word, or token or type. Any other question from anybody?
Yes, sir. I have one question. So, in that stacked, multi-stacked one, can you please explain how the back propagation works? So, do we calculate loss at the last layer, or we calculate at each and every layer?
At the last layer.
Okay,
Because we are
and
not
this.
doing the prediction here. We are getting the final representation. Based on that, we are doing the prediction. What is the next word, or what is the previous word? Okay. So the loss we know only after it has passed through all the layers, and we have applied that other small architecture to get the next
Okay.
word. Then we backpropagate and update the parameters of all these components.
So at layer 1 there is this bidirectional things happening, right? So my question is, do we complete this whole sentence prediction at layer 1, then we do the whole sentence prediction at layer 2, or it is word wise and it goes parallel in the one stack?
Not parallel. So earlier we had one RNN. Now
Yeah.
this is the entire multi-layer RNN.
Yes.
So we get the input. We give the input here. And suppose we are doing the next word prediction task. After we get the fused representation here, from here we do the prediction of the next word, not at intermediate levels.
Okay. Okay. And at every like one layer, it has this hidden representation from the previous RNN enrolled in the time, right? Because back propagation happens through time. So I'm like at one layer, how it all the layer goes in.
For every token, we see every token, like my favorite season is spring. So my favorite season. So when we had the word my, we got this representation, we predicted the next word. Now, when we get the favorite, we know we have seen that context my favorite, we try to predict the next word. My favorite
Yeah, that I
season, we try to
understand.
predict the next word. So for every token, that is after unrolling for every time step, we make a prediction and we update the things. So this is the H0. Here we have the representation from the first layer, H1. Here we have the representation from the second layer. Sorry, H0, H1, H2.
Yeah, got it, sir.
And H3. So final prediction will be based on, and then this H can be a combination of all these. Final prediction will be based on this H. So we must have H0, H1, H2, H3 already computed.
Mhm. So in your final presentation, we have two representation, one from forward, one from backward, right? Which one do we select? Do we combine both in some way?
Both. So that's what we see here. Forward
How
and
do we,
backward.
is it just the concat?
And that's the most common choice. Yeah, concat. So here also we, in the next diagram also. So this one and this one. So dark red and dark purple. So that becomes the representation from layer 2. Light red, light purple, that becomes the representation from layer 1. And green is the same for both. That is for. So
Okay,
concatenation is the most common choice. Yeah.
got it. Thank you, sir.
Will Elmo be able to handle the auto vocabulary words? Still.
Out of vocabulary, no. Because the initial thing that it gets, I mean, you need to do special consideration for that.
Mm-hmm.
Okay, so then, yeah, Elmo can be integrated into almost all neural NLP tasks with simple concatenation to the embedding layer. So yeah, so what they said is that, again, here also the Elmo representation you can combine with other representations, and then you can, yeah, you can actually enhance the inputs for that. And what they have shown is that across multiple tasks, they have seen, this paper came in 2018. So till 2017, whatever was the best performing model for different tasks, and they were able to perform better than that. So for example, these are the different tasks, and these were the different scores for them. And they started with a baseline which has an inferior performance with the SOTA, state of the art. So everywhere the values were smaller. Here it was equal, but yeah. And then what they did is that they applied Elmo there. So if these were some neural architectures operating on some representations. So they retained the architecture but fed the Elmo representations, and they saw that the performance increased. And these are the relative, these are the absolute improvements, and these are the relative improvements. So it is what they showed is that this Elmo representations can actually be good representations, and whatever architecture you use, instead of using the, I mean, you can just modify the representations that these models work on, and you'll get better results. And this is not for one task, across multiple tasks. So Squad is Stanford question answering dataset. So there you have a passage, you have a question, this is the input, and the output is the answer for that question. Then SNLI, Stanford NLI. So here you have a couple of sentences. The first one is called premise. The second one is called hypothesis. So based on the premise, the hypothesis can be entailed. So we can follow the premise. For example, it is raining outside. Second sentence is I am carrying an umbrella. So second sentence can be entailed by the first sentence. And this is one example. They can contradict also. Like it is raining outside and the sun is shining brightly. This is a contradiction. And there could be some a different, and the sentence can be unrelated, completely unrelated also. Say it is raining outside and what to agree is a non-contextual embedding, unrelated. So as an input, we have a premise and hypothesis pair, and output can be either entailment or contradiction or neutral and unrelated. Then there is something called semantic role labeling. So given a sentence, identify the role that is played by a word. So word can be a subject, which is the main agent performing an action. It can be an object which is receiving the action. Like I think in the previous class we gave an example like Tom broke the window with a hammer. So the window is the object that is receiving the output of the, receiving the impact of the action. Then Tom is the person who is performing the action. So the what is the role, semantic role for each word? So that is semantic role labeling. Then there is a co-reference resolution. So we also talked about co-reference chain possibly in one of the earlier lectures. See, the new model was released today. It has better, larger RAM. The memory is, the available memory is at least 64 GB. So model and it, they refer to the same thing. RAM and memory, they refer to the same thing. So these are the different co-references. So this co-reference identification is another task. It is a little difficult task as opposed to the other one. So that's why the performance is also, I mean, this number is also quite low than the other numbers. Then named entity recognition, then sentiment tree bank, these things. And then, so across different tasks, when they see that, okay, you can just plug in Elmo representation and you can get a big boost in the performance. That means the representation is powerful. So that was the conclusion from this result and became very popular. Okay, now here we talked about contextual representations, and but then how do we measure contextuality? So suppose there are two different models and both of them are saying, okay, we give contextual representations. So which one will you prefer? So one can say that, okay, we apply it on different downstream tasks and see which one is giving better performance and which one, the one which is doing better, we say that, okay, that gives better contextual representation. But that may not be a direct indicator of the contextuality, because it says is that these representations are better. Okay, and hopefully these representations are better because they consider contextuality, but we are not able to directly measure the contextuality. So there were a few work, not too many, that talk about measuring of the contextuality directly. See, we talk about organic farming and we see many products now which have the label as organic, but we don't really know whether it is organic or not, right? So is there a way in which we can certify that, okay, this is contextual representation? So word in different contexts should not have similar representation. So that is the very first thing that we expect, right? So if the same word that is appearing in different contexts, every time its representation should be different, or there should not be two similar representations. Now suppose there is a word which is present in n sentences, S1 to Sn, and the position of the word in these sentences are I1, I2, I3, In. Here I'm assuming that each word is appearing in one sentence only once. If it occurs multiple times, it can be handled easily. So suppose S1, S2, S3, these three sentences are context is key, I lost the key, generated necessary is key pair. And so this is S1, this is S2, this is S3. And position of the word in these sentences, I1, I2, I3. So I1 is 3, it's the third word. S2 is 4, it's the fourth word here. And S3 is again 4 because key is the fourth word here. And our word under consideration is the word key. Now, if LSI is a function that maps SI, what is SI? Ith word is sentence S. So it maps SI to its representation in the layer L of the model F. Okay, so if it is the Elmo model, then F is Elmo, and suppose there are 3 layers, so Elmo layer 1, Elmo layer 2, Elmo layer 3. Okay. So FL means F1, F2, F3, and S comma I. So it maps SI to its representation, and we measure something called intrasim. What is intrasim? Here we vary I, so this one is changing. We fix the layer intrasim LS. So for this sentence, for this layer, these two are fixed, L and S we are fixing. It says that you vary your I. So I equal to 0 means this one, I equal to 1 is this one, I equal to 2 is this one, I equal to 3 is this one. So for this sentence, you get the representation from LH layer of the model, and you compare that representation with the representation of the overall sentence that you get from here. Typically, the representation of the overall sentence can be obtained by taking the average of representation of the individual words. And you find this similarity as a cosine similarity, and then you get the overall summation or average of the cosine similarity. So this one will have the representation of S1. So from this layer, whatever representation we get for S1, with that we'll find the representation of the word context. Again, with the same thing, we'll get the cosine similarity with the word is. Again, with that same sentence representation from this layer, we get the cosine similarity of the word key. So all these similarities.
Is the dimension of the SL is 1 cross n, and FL of this function is also 1 cross n, right? So there are 2 vectors, and then we are finding out
Yes.
the cosine similarity, right?
Correct. Yes. So this is cosine. This is also cosine. And this is also cosine. Now you take the average of this. So average of this, and that will give you this intrasim. So it tries to measure that, inside a sentence, whatever words are there, there should be some relation among them. They should be connected with each other. So that's why this intrasim, internally each word should have a reasonably high. It should not be too high. Then the model may be forced to learn same representation for everybody. No, not like that. but it should actually be high. So that is the first thing. And then they have something called self-sim. Self-sim, the self means the same word, or yeah, here the word is key. Now here we're fixing the word and also the layer. So what we are doing here is representation obtained from layer L of the module for the word, this word from the jth sentence. So if you remember, S1 I1 is that contextual word key, S2 I2 is that contextual word key, S3 I3 is the contextual word key. So you get each of these occurrences, a representation of each of these tokens. And so this representation that you get, say S1's key, this is the representation. S2's key, this is the representation. You get the cosine similarity between them. So this k not equal to j, what does it tell? That Sj and Sk and j not equal to k means these sentences are different. So you are getting the word from different sentences. So this key from here, this key from here. We are passing it through the model in a specific layer, and we're getting the representations, and we are finding the cosine similarity between them. And this we are doing over all j's. So finally, what happens is these we expect to be dissimilar, right? So we prefer lesser value here. And this is 1 by n square minus n. Can anybody explain why do we have 1 by n square minus n here?
I think it is total number of combination n and n minus 1.
Okay, and can you explain this part? Total number of combinations. What combinations are we talking about?
The combinations of different representations.
Right. So here our focus word is key, that contextual word. So this key is appearing in n sentences, right? For each sentence, we're getting one representation. So for n sentences, yeah, for each sentence we'll get one representation. For n sentences, we'll get n such representations. And we are trying to find similarity between each pair of these representations. And we hope that, okay, if it is coming from the meanings are different, and yeah, so the representations will be different. So for each of those pairs, we identify the cosine similarity and take the average. So this is how this n square minus n is coming. So this is one way in which contextuality can be measured for different layers. If you go to this layer to this layer to this layer, hopefully this we get more closer to the meaning space, semantic space, as we go higher. So yeah, hopefully with increasing L, this also would increase. I mean, yeah, that can be the expectation.
Sir, in that case, should the denominator be NC2?
NC2.
Yeah.
Yeah,
Because we are comparing key in S1, S2, S1, S3, then S2, S3.
Yeah, I also think so. It will be n into n minus 1 by 2.
it should be n into n minus 1 by 2.
Sir, I think probably it is NP2 because of probably they are considering unordered combinations because of different layers. Can it be so?
So when we say that, okay, if we say, suppose our j is 1 and k is 2, we are talking about first sentence and second sentence. So we are comparing representation of this and this. So j is 1, k is 2. Now our k can be 1 and j can be 2. So we are actually double counting the same thing. The cosine similarity is symmetric in nature. So the same thing is being considered 2 times. So
Okay.
ordering wise, things will be same, but yeah, it would have more sense if we have this 2 by this thing, and it's not only k not equal to j, k not equal k less than j we can have here. Other way, k not equal to j means 1 2 and 2 1. We are both these we are considering. So essentially, we are repeating the computation. Okay, so that is about
So,
yeah.
sorry, I just have a question, sir. Sir, for measuring this contextual awareness, this self-sim should be as low as possible. Is that a right statement?
Right.
So in that case, even when the embeddings are bad, the self-sim would be very low. In fact, it'll be the lowest when the embeddings are bad, right?
Yeah, but
So,
at that point, so essentially we need to look at both intrasim. The intrasim also will take a hit.
okay.
Since we are using cosine similarity, will these metrics not be affected by curse of dimensionality?
Dimensionality will play a role. Dimensionality will play a role. If we have very large vectors, then yes, the dimensionality will definitely play a role, even though we are using cosine similarity.
Yeah, so in NLP problems, mostly we deal with the very high dimensions. So we have any alternative metrics or reliable metric for such high dimensional representations?
So what happened is, uh, 1 second. So this was from 2019. After that, there might be some other works also which have come out, so that I have not checked in detail. But the other thing that could be like you compress that representation to a lower dimensional space and then fit to cosine similarity. But again, in that case, if we get a very high or very low score in that compressed space, we're not sure that whether the same thing can hold true if we go to the earlier original representation space. So that's one. Other thing could be like, so essentially the similarity function that we are using, this similarity can be measured in different ways. So if we can explore different similarity functions, better similarity functions, maybe the same framework can be used, but with a different similarity function. Yeah, so in many cases, if some scaling can be done or some further projection can be done, those would be some choices. But yeah, there can be some better choices too.
Okay. Got it.
And sir, can we use this as a loss function to force the model to learn the contextuality?
You can, and remember one thing, that the set over which we evaluate, that set has to be manually curated in order to uh, in order to ensure that the meanings in different sentences are indeed contextually different. Once we have it,
Uh,
then we can try to enforce this one.
Okay. Thank you, sir.
Okay, so next one, what's the time? 9:15. Then let us do one thing. Let us go for a 15-minute break now. We'll come back at 9:30. Okay, so we are ready to resume our discussion. So to start with, we'll be releasing the first assignment today. And each assignment, so it will be a group assignment. Each group can contain a maximum 2 members. So what you can do, so we'll also share a Google Sheet with you where you can enter the group composition information. Okay, so that is something that we'll be sharing, and also the assignment problem statement we'll be sharing, and we'll let you know the submission mechanism. So this assignment is based on language modeling, and so later on we'll discuss in detail about blue score and so on. So essentially that is used to compare how aligned two different text sequences are. So measuring similarity between text is important in NLP. And if X and Y are 2 sentences, then we compute something called modified n-gram precision. And that precision can be computed using this formula. Okay, so suppose we take n equal to 1, that is, it becomes unigram. So for all unigram which is there in X, you count how many times it is there, and you count how many times it is there in the other sentence also, Y. You take the minimum of these 2 counts, so that becomes the numerator, and the denominator becomes in the first sentence how many times it is occurring. So it's not a symmetric measure, and it's an asymmetric measure. And this n can be varied from 1, 2, 3, 4 like that. So this is about n-gram precision, and blue score can be computed using this formula. So we know what is P that we have computed just on here. Wn is a weight associated with the n value. Okay, so we can say that okay, unigram has lesser weight, bigram has more weight. So accordingly, Wn can be adjusted. But for the purpose of this assignment, you can assume that n equal to 4. That is, we go on till 4 grams, and Wn is equal to 1 by n. That is every choice of gram. That is n equal to 1, 2, 3, 4. For each of them, the weight is same, 1 by 4. And if that is there, then blue score can be computed like this, where BP is another parameter, which is called brevity penalty. And here we'll use BP is equal to 1. So as if this part is not there. So what you have to do is you have to implement this metric. It's a very simple task, and pre-process the text by lowercasing the text and removing punctuations, and using this implementation to find use this implementation to find blue score where X is this and Y is this. And then you have to, there are a couple of questions that you have to answer. So is there any doubt regarding the assignment?
What is the text we are data set that we have taken into account?
Why do you need a data set here?
Okay, so
Implement blue score
Yeah.
metric. And
yeah,
what
yeah.
is blue? Yeah.
Yeah.
Sir, in the fourth part, we can have any pair of 5 sentences
Yes.
of our choice.
Right. You can give interesting sentences, huh? So that's up to you. Okay, so this one we will share, and also I'll share a Google Sheet where you can enter your group composition information. These 2 will be uploaded today. Okay, now
Sir,
let me.
one
Yes.
question I have, sir. So on the formula, when we say count X n gram and count Y n gram, So n-gram is like suppose we are considering bigram. So are we x is the count, x is your x sentence, right? Sentence x. In that sentence, are we counting how many n-grams are there? What does it mean actually?
So for an n-gram in the sentence, how many times it is occurring? It's not total overall how many n-grams, not that, but
In a
for
sentence.
each unique n-gram in a sentence, it is the
Oh,
count.
unique n-gram in the sentence. Oh, okay. So it is unique n-gram in that sentence.
Right. Otherwise,
Yeah.
you know, if you have a sentence of n words, it will always have n-1 bigrams.
Yeah. Yeah. That's what I was thinking. Okay. Yeah.
And
then it makes sense.
so this paper which introduced blue is also mentioned here. You can also have a look at that.
Okay. Yeah. Thank you.
Okay.
Only one
So
question is there.
only one.
Thank you.
There's only one. And since it's a simple one, we'll have a 1 week deadline for this assignment. Okay, now let me go to the okay, so let us move forward in our discussion now. So next topic that we'll be taking up is called transformers. So what we saw is that in Elmo and RNN and so on, so we have sequential connections, right? So if you remember in Elmo, we had this bidirectional LSTM. So this can be computed only after. So this can be computed only after this is over. This can be computed only after all the LSTM cells previous to this, they are done, time based unrolling. So that's because of how RNNs work. So you need the previous context to know the current output for the current input. So we need to wait for all previous contents to be seen before we can move forward. So that, although the performance is good, but that poses a major challenge in training the network. So if you look at the language model objective that we showed here, and 1 billion English word benchmark. So if we have a larger collection, that means more number of next word predictions to be done, more number of language modeling, this objective function to be computed for more number of times. And every time you have a long sequential dependency like this, the training becomes very, very slow. So then automatically the next question was, is there a way in which we can make it faster? But again, RNN by its own nature will work like that. So we cannot do a lot there. So then there was a requirement to look at alternative choices so that we can retain that sequential information. We can still retain that contextual information somehow, but we should be able to do faster. So can we remove these sequential connections? Okay, these connections can be removed. So if we remove all these, now these things become isolated, not connected to anybody, right? Then how do we capture the dependence on the contextual information? Now that dependence, then they said we can capture by doing some interesting stuff, and that will be called attention. So essentially what will happen is that for each word, so we say that this word's representation, if we consider the bidirectional LSTM or bidirectional RNN, will be influenced by the words before it and after it, right? Not words, the tokens before it and after it. Now, can we do it more explicitly by checking, by comparing each token before it and after it with this token explicitly? So how strongly connected this word is with this word, or this token is with this token, this token, this token, this token. So if we can directly capture that, then we do not need the sequential connections. So this was actually a major enabler for the transformer architecture, which enables a much faster processing of the sequences. So this is the transformer model. So we'll talk about the transformer model. Here we have encoder and decoder. We'll see what they are. It was trained for the machine translation task, and it was shown to be very, very good. And then the architecture have been used for many other tasks, the transformer blocks. So the central part of this is that how do we measure the affinity or attention of this word with all other words? So this attention is essentially captured using some vectors. So each token in this network has 3 different representations associated with it. One is called query, another key, and value. So they are also called Q, K, and V. So the role of that we'll explain when we go in detail the computations that happen. Now for a given word, its representation will be governed by the value vectors of similar vectors. So what does it mean? So set the temperature to high. So the representation of the word temperature will be governed by these, how similar, identify the similar vectors. Okay, so what identify, that means identifying some similarity, and then take a weighted combination of the vector values for those words, and the weights are the similarity weights. Okay. So if we write like this, so if this word has V, and this is V1, this is V2, this is V3, this is V4, and this is V5. So, and suppose the similarities are similarity of set with V3 is S13, this is S23, this is S43, this is S45. Then the final representation of V, the modified representation of V3 would be like the summation of Vi Si3, a weighted combination of the value vectors with the similar vectors. So that's what is written here. For a given word, its representation will be governed by the value vectors of the similar vectors. Okay, now how do we, the value vectors we know it comes from here, but how do we identify the similarities? So what we do is take a word and get its query vector. So for the word temperature, we get its query vector. So for temperature, we have the query key and value. Get similar keys. So that means, this is, here we have Q, K, V for temperature. For all other words also, we have this Q, K, and V. Now for all other words, we compare the current words Q with all other words K. Okay, suppose this is the K vector for set. This is the K vector for the. This is the K vector for 2. is the k vector for I. Okay, so this q vector, with that we identify the similarities of all other vectors. And how can we identify the similarity? Because we only take the dot product. Okay, and this gives us S1, S2, S4, S5, like we have written here. Okay, now since these are coming using dot product, they can be, dot product means just element wise multiplication and addition. Only that. So they can be unrestricted, they can be, arbitrarily positive and arbitrarily negative. So what we do is we can apply softmax on it so that these scores can give us, can be converted to some weights, so that the weights are all positive and they sum to 1. So that's what we are doing. So this should be dot, this also should be dot, this q dot k, this one we compute, and then we take the exponential of that. Next, we divide, we just normalize that one. If this is the similarity weight, we multiply the tokens value with this similarity weight over all other words, I, all other tokens. Now, this is the final vector after this refinement for the word under consideration. So this part is okay. And we can do it element wise, we can do it one after other for each word, like q dot k1, q dot k2, q dot k3, q dot k4. But since it is dot product, we can actually combine all these k1, k2, k3, k4 and have a matrix. Consider this as a matrix, and we can use a matrix operation q dot kt, q dot k transpose. If we are having transpose, then it should be like this, and this is q. So this is q, this is k. K transpose means it will become like this. Now when we do k transpose, essentially this one gets multiplied with this column, q again gets multiplied with this column, this column, this column, and finally we'll have the different scores. Now they also added a denominator here, square root of dk. So this one is for some scaling. Okay? So this is called this is a scaling factor that they do to control this dot product. Okay, so even before softmax is applied, when we finalize this q dot k, so that means we still do not apply the exponential part. So this q dot k can actually become very large. And remember, so all these representation schemes typically use very large dimensional vector space. So in BERT they use 768, I mean the base model. Now actually this 768, and then if we do a multiplication, I mean element wise multiplication addition, so this can actually be very large. So we have many very large vectors, and then we have softmax on that. So it might be better to regulate the value somehow. So that is obtained by doing a division here by square root of dk. So again, d is the dimensionality for the key vector. Dk is the dimensionality for the key vector. So if it is 768, then it is square root of 7. If dk is 768, then we are dividing by square root of 768. So the idea here is that we want to control or regulate the values. But again, instead of dividing by dk, because again everything will be too low there, we can do some adjustment and divide by square root of dk. So this is about the attention. It's called scaled dot product attention because this part is nothing but the scaling. And here the numerator, we are having dot product. And this finally is the attention score with which we are multiplying the value vector to get the final representation of this word. of this token transformer under consideration. Is there any doubt here?
Sir, what does this query key and value represent?
So these are three different representations associated with each word. So this query is used for matching with others. So when we try to match, what are the other words which are similar to me, or what are the similarity score of other words with me? So we actually are sending a query. So that is the query vector. Then the key vector, like we have the key value pair and something, the key value becomes some identity of the vectors of those words. So this key is used only to match with the query. So if you remember in what to vec, we have this target and context representation, right? So these can be two, I mean, here it's something like three different representations. So query is my own identity that will be used when I compare myself with others. Key is my identity when I will be compared with others by some other, which will be initiated by some other word. And value is my final representation, which will be, which is my final representation actually. So Q and K are only used for this matching purpose, and V is the vector, which is the final representation. So this attention or similarity score is based on Q and K, but finally, after the similarity score is done, we use this V. So that is the role which Q, K, and V play. So initially, if you so we'll look at how that works. So initially, for each word, we can get a word-to-vec representation, and this word-to-vec representation we can multiply. Suppose this is X. This X we multiply with WQ, or randomly initialized matrix, to get Q. We multiply X with another randomly initialized matrix WK to get K, and another matrix V, WV, to get V. So they originate from the same thing, but these matrices WQ, WK, WV are different, and we get three different representations.
Sir, a couple of questions here. So here in the representation which you drawn, the k values are or the k key vectors, right? They are specific to the words. However, q seems common across the words. Is that the
No,
case?
no, Q.
Okay, so
Q
okay,
is
this
also
is the
different for each word.
q set for k set and q the for k the. Is it like that?
Right. Each word has Q, K, and V. Now,
Okay.
in this example, I want to refine my representation of temperature. So for the temperature, I get the Q vector, and I compare it with the K vector for set the to high, and that gives us the similarity values S1, 3, S2, 3, S4, 3, S4, 5. Then I apply softmax so that this becomes a kind of probability weights, and then with this we multiply the individual value vectors to get the final representation of this one.
Yeah. Yeah. And sir, about scaling. So we are doing scaling to reduce the parameters, right? Like to reduce the high values, high number of values. So we are doing the normalization also in the above step. Why this scaling is additionally required, right? Normalization is also in the first step, it is also averaging and reducing sort of volume.
Right. So, if this Q dot key, everything is very high, if all these values are very high, and then if you do a softmax, then you will see that things may become very uniform. So in order to, initially, so let me refer to the paper where they introduce this one, the scaling part. So if everything becomes very high, then softmax also will not be able to, distinguish a lot. Say, for example, you have X and AX. A is a scalar. When you raise this to exponential, this becomes e power x, this becomes e power ax. And e power ax is nothing but e power x power a. So this becomes actually very large and there might be very less control available with us if we do softmax on large values. So before only we try to divide by some constant so that this becomes slightly manageable.
Sir, is Q and K also contextual?
Yes.
So for value, it is clear that we are taking attention to make it contextual. But how do we do it for query and key?
So attention function works like this, and Q and K are adjusted during backpropagation.
The screen is not being shared.
Yeah, I'm just opening a different document.
Okay.
Share that one.
So if two words are similar in context, then their all Q, K will be similar.
Not really. No, so it's not based on only one. It's not based on only one instance, right? These are trained over a very large collection. So there may be deviations.
Like for synonyms, if two synonyms are used in similar context, then what can we say about their Q, K, V?
So if those synonyms are observed over a large collection many times, then we can expect that. So this is the paper. It's called "Attention is All You Need." It's from Google, mostly Google research. And let me use the background. Attention function, which is mapping a query and a set of key value pairs to an output. The query keys, values, and output are all vectors. The output is computed as a weighted sum of the values, where the weight is assigned to each value. It is computed by a compatibility function for the query with the corresponding key. Now this compatibility function is also that attention function. So they used scaled dot product attention. So input consists of queries and keys of dimension dk and values of dimension dv. Now they can be both. I mean, dk and dv can be same. We compute the dot products of the query with all keys. Okay, that q vector with all keys from all surrounding words. Divide by square root of dk and apply a softmax to obtain the weights on the value. Okay. In practice, we compute the attention function on set of queries simultaneously, packed together in a matrix Q. Okay. Yeah, keys and values are also in K and V, and this is the function. So they, for attention functions, they also considered additive attention and dot product attention. So dot product is identical, but they have used the scaling, except for the scaling factor, this one. Additive attention, with that they have compared. Dot product attention is much faster and more space efficient and can be implemented using highly optimized matrix multiplication. And for small values of dk, two mechanisms perform similarly, where so dot product growing large in magnitude has some problem. So that pushes the softened function into regions which also affects the gradients. So that's why they want to regulate the dot products, and that regulation is done by this one, scaling factor of 1 by square root of dk.
Sir,
So,
from Q and go ahead.
yeah, so we scale the dot products by 1 by square root of dk.
I have one question here. So we multiply this query and key, right? And we already got the similarity. So now why do we need to multiply with this new v and we call it value? What extra thing we are bringing here? Similarity we got from these two things, right?
Yeah, this is a similarity, but we want the similar vectors to influence the final vector. Right, so that's why we multiply and take a weighted combination. Similarity is simply the weight.
Oh, okay, yeah.
A scalar weight.
Okay.
So this is shown here pictorially. So Q and K we multiply them, matrix multiplication. So we get Q dot K or QK transpose. Then we scale. And is optional masking. We'll talk about that. For the time being, you ignore it. And then we do a softmax. Right? So that is this formula. And then we do matrix multiplication with V. So this QK multiplication, scaling, softmax, it gives the weights. These weights are scalar, but with these scalar weights, we multiply the corresponding value functions and then take the similarity. So if you are familiar with the database terminology, suppose we have this query so we have a query and we have a database of Q, K, and V. I'm ignoring the Q column, only writing the K and V columns. Now suppose I want to select everything that is similar to this or same as this. In database, we will write that select star from table where K equal to Q. Right? So what that will give us is only the row for which this Q and K are matching. Or we can write select V from table where Q equal to K. But now what we are interested in is not only one entry, because it may not match also. We get everything which is similar. Or you can say that instead of doing an exact match, we do a similarity match, fuzzy match. So select star or select V from table where Q dot K is something. But again, instead of thresholding, say select everything, but you denote the similarity score. In earlier case, this similarity was 1, everything else was 0. And here, everything is between 0 and 1 and is affine weight. Now, instead of V, which was earlier coming from only this row, we'll also take V, but we'll take a weighted combination. This one, then for this one. So this is another way of viewing at the of viewing that attention computation and the similarity. So layer by layer, this V vector gets modified, and the Q and K they get modified during the backpropagation because they associate with metrics. So changes. Now this was there, and they said that again these were some engineering choices that were made by people. Even you can say, why do we need 3 vectors? Can't we do it with 2 vectors and all that? Why do we need query and key? Can't we have only query or only key? So those are all possibilities, but they this very large architecture on very large data, they have showed that this thing works well. And then people started following, okay, then let us use it, because the pre-trained models were also released. Then one can directly make use of that. And once somebody starts making use of the pre-trained model, they have to use that QKB, whatever has been used here. So that was how they did. Well, most likely they would have tried with Q and K or K or V kind of things also. But yeah, this is the thing that they finally found out to be working really well. So, and another idea that they had is that, see, this WQ, WK, WV, these things we mentioned, they all are initialized randomly. Now, one random initialization will take us in one path and give one model state, right, to all parameters. If the random initialization was different, maybe we would get something else, because here everything is self-supervised objective. Well, sorry, let me take back that comment. We'll come to it later. Objective function will come later. So yeah, so idea is that instead of having one WQ, one WK, one WV, we can replicate it. We can have multiple such instances of WQ, WK, WV. And each such a replication gives us one more view of that model. So these things they called heads. So instead of one head, they have multi-head. Multiple head means from one head, we get one VKQ vector for a word. From another head, we get another VKQ vector for a word, and so on. And finally, we can actually fuse them. So for fusing, they used simple concatenation. Okay. So this is cell. So V, K, and Q, they come together through dot product attention. And these V vectors, K vectors, Q, so these vectors as well as this dot product attention can be replicated. Exact same operations happen, but only with different initializations of WQ, WK, and WE. So this is called multi-head attention in transformers. Any queries here you can ask.
So multi-head essentially means for the same set of inputs only, right? But different initializations.
Right.
Okay.
Now this is the attention function. Now this transformer architecture is actually there are many things there. Attention is a core component. So once we have understood what attention is, we can possibly try to see what happens in the transformer specifically for language modeling tasks. So suppose a cat sat on the mat is full stop, then end of sentence is the input. So for scale dot product attention, what happens is that suppose for the word A, this was the initial representation, and we want to know the modified representation after this scaled dot product attention. It is also called self attention. Each word is compared with every other word, and this word also will be compared with every other word, and so on. See, what we do is we compute this weight. So this weight, these are nothing but the softmax parts, and these are the V's. They are the V's. So we combine this attention and V, attention and V, attention and V like that. Now, okay, sorry. So that was this part. What I showed in the earlier slide was this part, and then you apply softmax. Now these are the weights. These are scalar weights. With these scalar weights, you multiply these value vectors, and you get the final vector for the word. Okay. So this is the final vector. Now we get this one. Now we go to the next word. Cat. For cat, we again find the dot products. That dot products, from that dot products we get the similarity weights, and then we take the weighted combination to get the final representation, and we keep doing this for all different. Each word that we get or each representation that we get, that becomes the output from this layer. So these are the update representation for each word from this one layer, and we can stack multiple layers one on top of the previous one. So again, we are having a multi-layered architecture, and okay, now, so that is the multi-head attention part. Now, multi-head attention is a part of the transformer block. This transformer block has other components also. So each block has two sub-layers. Okay, one is multi-head attention that we have just explained. And the second one is the layer feedward neural net with ReLU. So after multi-head attention, I mean, this was the input and this was the output of the multi-head attention. So input was there, we get output, and this we pass to a feed-forward neural network. So there should be the complete diagram somewhere. And each of these also has a residual connection and layer norm. So these are the residual connections. So output is also added with a fraction of the input. And there is some normalization which is also done. So layer norm changes the input to have mean zero and variance one per layer and per training point. So for each training point, if it has multiple dimensions, it makes it zero mean and unit variance. That is done by, you can find the mean, then you can subtract the mean from each component, and you can then divide by the standard deviation like this. So this is a standard practice, and people have seen that this makes the neural network more stable. So this happens in each layer. We'll come to the entire diagram it's there in one of the future slides.
Sir, I just have a question.
Yeah.
Sir, in the previous slide, we talked about layer norm. So what's the difference between a conventional patch norm and a layer norm?
So there changes the input to have mean zero and variance one per layer and per training point. Per training point also it happens. Okay, so each training point, if it is having a 768 dimensional vector, so that each vector will have zero mean and unit standard deviation. It's a
So
training point
that
level,
means,
not batch level.
okay, so across time steps and across dimensions, the mean is calculated, is it? Mean and the standard deviation.
Yeah, so we do not have a concept of time step here, but for each input, this will be there.
Sure. I mean, when I say time steps, assuming that it's a sentence, if each word is considered a time step, then all of them are given at once simultaneously as input to the model, right?
Mm-hmm.
So if I consider dimension 0 as the token, so this mean value is computed per dimension across all of the words, so that we
Right.
get, yeah, a mean vector 1 per each dimension, is it?
Right. So this I'll clarify in the next slide. I'll just cross check on this one. So input. So this is the input. This input here sequence of different representations, and this sequence, if we consider it to be a matrix, this one has mean zero and variance one. This entire sequence should have not each token, but that entire sequence as a whole. This I'll check and get back.
Sure.
Sir, output of the layer norm is the number of words we have, right? And now this feed forward, do we have, I mean, how feed forward is working? Is it taking all the input parallelly or same weight is shared across all the inputs?
Same weight is shared across all the inputs. Yes, the parameters are, yeah, because number of tokens will vary. Yeah, it's the same.
Okay.
So if you remember, when we clicked the sequential connection, somehow we lost the positional information. Right? So they did some attempt to include the positional information by including something called positional embedding. So suppose we have a sentence, so where and suppose we number the positions, like position 0, position 1, position 2, position 3, like so position of each word, the offset. And this positional encoding, they chose to be a function like this. So this will become a vector. This is also a vector. So they alternate between sine and cos. So again, there is no very clear justification regarding why this should be used. Some justification will be there in the paper, but again, one can use other positional embeddings also. So whatever information about sequential information we had lost, they tried to include some of that using this one, because this embedding is depending on the position where it appears. So they added a positional encoding so that the same words at different locations have different overall representation. This is another thing. Now the same word is appearing at different locations. Word is same, but they're coming as different tokens. To start with only, they'll get a different representation by virtue of this positional encoding. And then they have a decoder. In the decoder, there are a couple of changes. There is masked decoder self-attention. So typically, the decoder is used to generate or decode one word at a time. Okay. So when we consider that language modeling objective for RNN, we had these decoders. So we had these predictions, right? Now these predictions will come from the decoder. So there is some state of the system. That state they'll try to convert. They'll try to transfer to a vocabulary space. And from that vocabulary space, they'll sample a word and give us the output. So that is the decoding part. Now, this decoding depends on the previous words. So it cannot see whatever it has not generated yet. So that's why we have a masked decoder self-attention. So set the temperature to high when we were looking at the similarity attention weight and the final vector computation. We found the similarity weight with both left side words as well as the right side words. But here, in case of masked decoder self-attention, it is typically used for generating a sequence. The decoder cannot observe the tokens that it has not generated yet. So that means even during the training, whatever right context is there, we mask it. We do not expose it to the model for computing attention. So that is masked decoder self-attention. It only depends on previous words. And this is one more important part is encoder decoder attention. The queries, they come from previous decoder layer and keys and values come from the encoder. Yeah. So uh, mm, this part, we'll see that this is a multi-head attention. So the attention function remains the same, but attention function has Q, K, and V, right? So Q and K come from the encoder side. This is the encoder. Left side is the encoder. Right side is the decoder. So Q and K, they come from the encoder side and value comes from the decoder side. Okay. So queries from previous, sorry, I'm sorry. So this is query and key and value come from encoder. So because I'm trying to generate the next word, so from the current thing, I'm trying to find out the similar things from the encoder side. So queries come from previous decoder state like this one, and keys and value come from encoder. Okay. So encoder, decoder, is encoder self-attention. So here for this one, we look at both from both left and right context. And masked decoder self-attention, when we compute for this, we look at this. When we compute for this, we look at this as well as this. And encoder decoder attention. So this part comes from decoder, this part comes from encoder. So here are the different words. For each word we take K and V from here, K and V from encoder, K and V from encoder, and we only take Q from the decoder. So why is it needed? Because the encoder decoder is tasks where based on some context we generate some output. So encoder is typically used to only represent the input. And from that encoded representation, we can do many things. If you remember Elmo, we fed one input and Elmo finally gave one representation for each token. Now, how to use that token, that we decided based on our task. So again, if you remember, there was a baseline, and to that baseline model, we fed these representations, right? So if it is something like textual entailment, so there for the first sentence, we'll get the representation for different tokens. Then suppose we take an aggregation over that to get one single representation for the entire sentence. For the second sentence also we do the same thing. And then we have another network component that takes these two things and finally determines whether it is a positive or negative, or entailment or a contradiction or unrelated or neutral. So if we want to have sentiment analysis, sentiment annotation, then what we can do is take an input, pass that to Elmo. For each token, we now get a final representation given by Elmo. We can aggregate them by averaging or whatever weighted averaging. And that single vector that we get, we can feed it to an MLP to predict the final level, right? So here we are interested in getting the representation of the input, and the final task could be like classification or regression or whatever, one single thing, and we are done. On the other hand, there can be tasks where we need to generate a sequence of tokens, like machine translation. This transformer was first introduced for machine translation only. Then in input, you have English, in the output, you have German. So it has to understand the English sentence. So that can happen through encoder. And then you have to start producing the German tokens. Now that will happen through decoder, not one token at a time. Now the masked decoder self-attention is there because you cannot see what has not been generated yet. So that's why the decoder self-attention can only look at the words that has been generated till now. And encoder decoder attention, what it will do is whatever has been generated till now, so that will come from decoder, and the complete English input that and the representation for the different tokens from there will come from the encoder. So it will try to understand what part of the input is not yet covered in my output. So that's where the encoder decoder self-attention helps. So in the encoder, since we have not started the decoding process yet, there is no point of getting the decoder samples from tokens from decoder. So it doesn't, an encoder is only for understanding or encoding the input. So that's why there is no cross attention, encoder decoder cross attention. But when we have represented the encoder representation the tokens from the input already, we have encoded them. And now we are doing our task of generating the output token by token. we need to look at the context which is coming from the encoder so that our generation is non-redundant and meaningful. So that's what is enforced by the encoder decoder attention, cross attention. So, so these are the two things which needed to be different in the decoder. Are there any questions here?
Yes, sir. So first question on this decoder part only, like here suppose your input is English and in the output here it says that shifted right. So I consider that the German sentence is output. Now how do we train this? Uh, is it like one by one word prediction or all the word predicted at once? Because it's a like we are giving all the input at once, right?
So the shifted right, that part gives the next word as the ground truth, so that we can find the ground truth. We can compute the loss function and update. So, so that's what shifted right is. However, the decoder needs to the decoder self attention needs to know what word has been generated
Mm.
at time t, so that it can do the generation in t plus 1. So that part will be sequential.
Oh, okay. So we provide all the input by encoding here English sentence and the output we do sequentially, and for each time we provide the masked attention on the German word based on the current word we are going to predict. Is that so?
Yes. Now internally things are optimized somehow that yeah, by inspecting the code we can tell, but it has to be a sequential process, because unless we know what has been generated in the previous step, we cannot use it in the attention computation for the next part.
Okay, and I have one question on the positional encoding. There we are using this periodic function. So we know that sine and cosine will repeat itself after some time. How we are covering that so that it doesn't get the again same positional encoding for the other words? And why didn't we use any other monotonically increasing function instead of periodic?
Again, this was some kind of choice. The again, very clear argument was not there, and just because we are dividing by something like this in the denominator, so these values are actually small. So sine and cosine, they will repeat after what, pi, right?
Yeah.
So they control that, and these values are small. The
Oh,
denominator is actually quite large.
okay, so it's like the making the resolution so high so that we get so many samples within that period itself so that it never repeats for the given input.
There might still be some pattern there, because sine and cosine, even if it's not complete repeat, there is some connection. Sine a plus b, you can have it as form, as a sine a plus b will be what, sine a sine b plus sine b sine b, something will be there, right? So
Yeah.
some strong connection will definitely be there. Some patterns will emerge.
Okay. Okay. Yeah. And for encoder and decoder, what are the specific tasks we can use encoder and decoder for here?
Yeah, we'll talk about that. We'll talk about that.
Thanks.
So suppose okay, so let us I mean, this was encoder decoder architecture for which can be used for natural language generation, natural language understanding tasks.
One question.
So yes.
In the decoder part, there is one output embedding, and towards the top there is one output probabilities. So these two things connected?
Decoder output embedding and probability. So output. Yes. So what happens is that we're generating the next word, right? So if this complete decoder, if you ignore this internal all these details, this decoder it will take it will output a vector. Now this vector will now from our task is generating a word. Now if you remember what we discussed when we used RNN for predicting the next word. So for the current word, it generates a vector after doing all these computations. But our task is to predict the word. Now this vector, then there are so many different words which are possible. So it applies a linear transformation on that. So this d-dimensional vector now becomes a v-dimensional vector. And then it applies softmax so that we have a probability distribution over the v different words. Now from these probability distribution samples a word. One can use a greedy decoding and say that the word for which the probability is highest will output that as our next word.
So that is
And
going
that
to be the output embedding.
for the next iteration, that will again come here. So if we consider that, okay, instead of English to German, suppose we are having English to Hindi, or say Hindi to English. So input is in Hindi. Now output is in Hindi. Now I am going to office. So after I am, suppose this is the distribution over the different words in the vocabulary. For going, suppose the next word was generated as going. Now the vector for going comes here as the input. Now the decoder has the vectors for I am going, and when I say vectors, Q, K, V, all these are there. And for the Hindi words also, complete मैं ऑफिस जा रहा हूँ उसका for that whatever input was there, we have a QKV representation for each of them. Now this is there in these three things are there in the decoder, whatever it has generated. These five things are there in the encoder. Now it will do a cross attention. I mean, I am going and मैं office जा रहा हूँ. Q, K, V, all these attentions will be computed and will try to get an embedding for the next word. Now from this again will this will be a d-dimensional vector. Again we'll project it to a v-dimensional space, and then we'll convert it to probabilities, and from that probability we'll sample the next word.
Sir, but this sequence length can be different. So
yes. So typically for this generation, there can be two things. One can keep generating till a maximum number of tokens has been reached, or a special stop symbol has been generated.
So these output embeddings are also learnable parameters.
Output embeddings are not parameters, but this generation of the output embedding involves some model parameters.
Output embedding is also going to be a d-dimensional vector, right?
The vector, but it's not a parameter.
Okay. Okay, so these are output embeddings these are the word which is already present, though whose vectorized versions are already present in the vocabulary.
Output embedding can be any embedding, and from that we'll try to predict the next word.
Okay.
See, if you have any dimensional vector, there are infinite such choices of vectors, right? Because we are talking about real number space. So we cannot say any embedding that we generate will exactly match one single embedding from the vocabulary. Suppose the vocabulary has only 30,000 words, but embeddings can be infinite. Okay. So we cannot match exactly. We need to go to a probability space and then sample from there.
Sir, while training this model, at that time, suppose we are creating German translation. So the output embedding will be the embeddings, word vector embedding or any kind of embedding for the German word itself, right? While training it, so that once we get the output probability, we calculate the loss and update the weights. And when we
loss
do the
function,
prediction, yeah,
go ahead.
So I was thinking that when we do the prediction, now we do not have the German word itself. So once we predict the first word, then we take that into the input and we create the embedding from that, because we know that how the embedding is created, and the same output goes to the now the shifted right input, and we get the next word. But while we do the training, we need to use our the German data set itself, right?
So training will have, so English word will be English sentence will be there, corresponding German will be there, and so it is easier for me to have some kind of Indian language here. So again, if we take the earlier मैं दफ्तर जा रहा हूँ and I'm going to office, first time it is generating I. And when we say generating I, essentially, how did it generate I? So before that, it got a probability distribution over that entire vocabulary space. So for I, there was some value. For am, there was some value.
Yeah.
In school, there was some value. For many other things, there were values. Now, but the target says the output should be I. So according to the target, the probability for I is 1, everything else is 0. Now we use the cross entropy loss.
Yeah, we already know the target, right? So the input, that shifted right outputs, that will be the target input itself at the training time, right?
Right.
And while prediction, we do not have that. Then we take the output probability and create the embedding and feed to the network.
Yes, we do that. Yeah.
Okay.
Sir, I have a question. So one of the reasons why we're doing this is because we want to learn context-aware representations for each of the words. So if I need to extract those representations, from which layer I will be able to do it? Should I be using query, key, or value?
You can get it from any layer. So we'll see that this nx means it can repeat a number of times. So this architecture, on top of that, can have n such layers. So in BERT, they have 12 layers. You can extract the representation from any layer. Mostly people use from the last layer.
Sure, sure. And specifically, it has to be the output of the feed forward block followed by the add and the norm, is it? That is the
Yes.
entire transform. Okay.
Right.
Okay.
So I'll come back to this slide. It connects with BERT. So this is the complete encoder decoder architecture for transformer, and the different different components are here. So those we have already explained. Now for BERT, what it does is, see, we saw that encoder and decoder, there are two parts. For BERT, they said we'd only use the encoder part. Okay, so our goal is to, we'll be mostly using it for natural language understanding purpose and not generation. If the generation is not needed, we do not need the decoder. We should be able to do only with the encoder side. So what they did is they took the encoder part and copied it, say 12 times. They stacked it 12 times on top of each other. So this is the BERT model. And so fine, that was the architecture. But how do we train and get the parameter values? So what they do is that they curated a couple of tasks. One task is that we'll have a pair of sentences. Or okay, suppose we have only one sentence. What we will do is I'll take that sentence, I'll randomly identify a few words from that sentence and mask them. Mask means I simply use a special token called mask. So if it was like I went to the store, instead of store, I'll remove store and put something like mask. And I'll tell the model to predict this mask word. So it's not so simple as that. So what they do is they identify maximum 15% tokens from here. And out of those tokens which have been identified, which have been marked for further processing, 80% of them they replace with the word mask. Okay, so went to the store. Suppose store is chosen to be processed, so store is replaced with mask. 10% of time they replace the word with a random token. So again, went to the store. Suppose the store was chosen for perturbation, so we replace it with a random word running. Then 10% of the times we'll remove it. We'll retain it. Went to the store will become went to the store. So that means we take an input, we identify 15% of tokens or 15% of positions from there, and 80% of them we change to mask. 10% of them we replace by random words, and 10% of them we just leave as it is. So this is the corruption part. We corrupt the input or noising part. Now the goal is that to predict the original text from the corrupted. So if it is the transformer encoder, so inside it can have a number of layers. So for each of the words, okay, we'll get an embedding from here. And for the words, for each word, then we can predict from each of these representations, we can predict what was the original thing here. Now, if I'm able to reconstruct the original sentence from this corrupted sentence, that means the model has been able to understand the language. Okay? So this is the one, this is the task. And then that is the, sorry. So there is a single sentence based denoising and prediction. And suppose we have two such sentences. And these sentences come from a large document collection. So when we talked about this RNN-based language modeling, we said that we have a large collection of documents. From there, we create the input instance and the target word, and we can train. Similarly, here also we have a large corpus to start with. We can identify different sentences from here or different segments from here. And for each segment, we can do this corruption and ask the model to denoise it or predict the original sentence. That can be one task. Another task is to identify, given a pair of sentences as input, whether they are next to each other. They were next to each other in the original collection or not. So this is very easy to, it's very easy to create such examples. Right? So you have a document collection. For each document, you split it into sentences, and you also note their positions like sentence 1, sentence 2, sentence 3, like that. So you can pick two consecutive sentences and the label is +1, and you can pick two sentences from the same document so that they are not consecutive and the label is -1. You can have two different sentences from two different documents and you can say that they are -1. So like that, using self-supervised manner, these instances can be created. And they use two special tokens. At the very beginning, they had a CLS token. And to separate two words, we are using pair of sentences, right? To separate two sentences, not words, in between they add separator. So input representation can have single sentence or pair of sentences. There are special tokens like CLS and SCP. CLS is typically added at the beginning, which is the pooled representation or aggregated representation for the entire thing. And separator separates the two input sentences. And objectives, masked language model, predicting the masked tokens. How good are we doing that? And next sentence prediction. It's a binary task. So now I think we can come to this diagram. So here, suppose there are two, we're going ahead with the masking and next sentence prediction. Sorry, next sentence prediction. So these are the position embedding for this complete input, position 0, 1, 2, 3, like that. And they are converted to positional embedding using the sine, cosine function, whatever. And till this separator, they are part of segment A. And after the separator, till this point, they are segment B. So we are having two different embeddings for the segments. The segment A, segment B, two different embeddings. And we have token embeddings for each token. Now these three things we sum, and that becomes the initial representation that goes into the encoder. And the expected outputs can be like, okay, so I mean, you can anticipate how the diagram and the expected output will look like. So it's the pre-training, masked sentence A, masked sentence B, and then we have a separator in between. We have a CLS token here. So from here we get the input initial representations, and finally, whatever the representation of the CLS token is, based on that, we do a next sentence prediction task. Binary. And for the masked tokens, we want to predict the original words. That becomes the masked language model objective. These two things combined can be the objective function for BERT. So this is called BERT. And this BERT is then used for fine tuning for other tasks. So this is with self supervision. It is called pre-training, and this is task specific supervision. Okay. So this is pre-training, which is for the language understanding based on the large corpora unlabeled data. But now I want to do it for question answering. So we talked about this squad data set, right? So passage is there, question is there. I want to find the answer. And with so for squad, the answer is actually a substring from the passage. So we need to give the start offset and the end offset. So from BERT, we can simply do that. Remember, we are not generating any tokens here. We are simply giving the offset, which is a number. We can do that. Named entity recognition. Yes. So here what we do is for each token, we have finally the representation. And from this representation, we identify which named entity it is. Then natural language inferencing is also there. So BERT, there should be a slide on the different performances of BERT. So they tried it on the glue benchmark. So for BERT, so this is MNLI, natural language inferencing. I explained the topic. So there are two datasets, matching and match and mismatch. So here the examples for premise and hypothesis come from same domain, and for mismatch it comes from different domain. Then QQP. So here we have duplicate question prediction. Then NLI, another natural language inferencing data, is sentiment tree bank. OLA, we'll talk about that in our next class. It's like how grammatically correct a sentence is. STS is for semantic textual similarity. MRPC, machine reading comprehension, passage comprehension. RT is again a textual entailment, but here we have slightly different from NLI in the sense that we have one hypothesis and one premise, and the label is they entail or do not entail. So contradiction and neutral, they are combined into negative class, and entailment is the positive class. So they saw that overall they are getting a good performance over across a large number of tasks. Are there any questions here?
Sir, this BERT training, this pre-training, do we take the transformer encoder here, wait also, or we start training from scratch?
So for pre-training, you can start from scratch. But if you want to take a pre-trained model and adapt it to your own domain specific collection, then you can take that pre-trained model and start further pre-training based on your domain.
Okay, and why does it call like bidirectional encoder?
Bidirectional because you are looking at both left and right context while doing the self-attention. Okay, so we'll take a short quiz now. So I have, it's a Google form based quiz. The link I have posted in the chat window. We have, yeah, it's a short quiz, 3 questions. In 10 minutes, try to conclude it.